In this video, we are going to talk about states of matter and how you can use everything you've learned throughout this unit to help you compare relative strengths of attractions within different molecules and how you can kind of compare melting points and boiling points. So when we talk about states, we're generally talking gas, liquid, and solid. We're not going to include aqueous because that involves putting something into water, and we're kind of concerned when something is just on its own, what state is it going to be? So what determines whether something is a gas or a liquid or solid obviously is partly the temperature, but if we consider room temperature, which in chemistry is 25 degrees, we know that different substances have different states, right? We're obviously breathing in oxygen, we're breathing out carbon dioxide, they're gases. We have water, which is a liquid. We have sugar, at room temperature, it is a solid, right? We have salt, at room temperature, it's a solid. So why are they different? The reason why they're different has to do with what type of attractions are holding them together. So when we look at what those different attractions are, they can be any of the following. So if I'm dealing with an ionic compound, then the strength of the attraction is how strong is that ionic bond, because that's what's holding it together. If I'm dealing with a network solid, I'm talking about covalent bonds, and how strong is that bond? If I'm dealing with a metal, then we're talking metallic bonds. If I'm dealing with something that's molecular, then I'm looking at the intramolecular forces. I'm looking at LDS, hydrogen bonds, and dipole-dipole. So when I'm trying to rank things or compare things, I have to be able to consider all of these different forces and determine which ones are present in my molecule. Because all of these different forces have different strengths. So knowing what force I have is going to allow for me to rank them. The other thing I have to be able to recognize is how strong my forces are when I'm dealing with different states of matter, right? So if you think back to last year when you were in Science 10, you spent some time looking at heating curves of water, right? So we saw that if we started with ice, we could heat it until 0 degrees, right? Which is when it's going to start to melt. So we're going to start to melt it, and then we can continue to heat it. And now it's turning into water, and the water is getting hotter and hotter and hotter. Then eventually we reach 100 degrees, or if we're in Calgary, which is where we are, we reach like 96 degrees, and it starts to boil. And we see that even though we're inputting energy, the state isn't changing until eventually it turns into a gas. So what's happening at these different stages are different things. So when we have a solid, we have really strong attractive forces. Our molecules or atoms are kind of locked into place. They're vibrating because molecules are always in motion. They're never not moving. If they ever stop moving, then we've probably reached absolute zero and we've made it occupy no space. But in the case of what we're looking at, in solids, they're vibrating in place, but the attractive forces between those molecules is so strong they're not able to break it. But as we continue to add heat or energy, we start to give those molecules a little bit more energy. They start to vibrate a little faster. Then we find that it starts to melt. And the reason it starts to melt is we've given it enough energy to now be able to start to break those attractive forces. So when we get into something that's a liquid, what we find is that our attractive forces form, but then our molecules have enough energy to break it. And they can move a bit, and then, they form a new attractive force with something else that's there. Then they break that one, they move a bit, and then they form a new attractive force, right? And that's how we can pour liquids, we can put things into liquids. But as we continue to heat that liquid, we give our molecules and atoms more and more energy. And eventually, we reach the point where it starts to evaporate. And when it evaporates, it turns into a gas, what's happening is we've now given our molecules enough energy to completely break all attractive forces. And now there's no more attraction between those molecules, and they're able to turn into a gas. So this is why we find that substances that are gases at room temperature tend to have relatively weak attractive forces. So it's easy for them to overcome it, which is why they're gas. if we think of a liquid, so water at room temperature, it has strong enough attractive forces that they are present, but it is weak enough that they're able to break and reform and break and reform. And then if we consider a solid at room temperature, these have really strong attractive forces. Our molecules or atoms do not have enough energy to be able to overcome it. So when we start talking about melting point and boiling point, it all comes down to how strong are the attractive forces. You're going to find that something with weaker attractive forces is going to melt or boil well before something that has stronger attractive forces. And that's because those stronger attractive forces are going to require more energy to actually be able to break them. So let me insert a couple of slides here. Hold on. If we are trying to rank or compare some substances, the steps we basically want to follow. So the first thing we want to do is we want to decide what type of molecule is it. So is it a network solid? Not network. So if it is a network solid, right, remember we talked about 3 of them. We talked about carbon, SiO2, and SiC. Okay, is it ionic, right? And generally we're recognizing ionic because we have that metal and non-metal. Right? We could also use our electronegativity numbers if we want to, but most of the time we can kind of decide from metal and non-metal. Is it metallic? If it's metallic, the formula is just a metal. Or is it molecular, right? So molecular would be all the rest of the covalent compounds that weren't contained in this. So once I decide which one it is, I might already be able to rank things. And that's because network solid has the strongest attractive force. To be able to melt a network solid, I have to break a covalent bond, which is the strongest of the bonds. If I have ionic, that's the next strongest type of attractive force. And that's because in an ionic molecule, we have whole charges at play, right? And if I had 2 ionics, I would want to look at what are the charge numbers, right? We're going to find that the bigger the charge numbers are, the stronger the attractions are going to be. So if I was comparing magnesium oxide to sodium chloride, because MgO has a +2 and a -2 charge, and the NaCl is a +1 and a -1, I'm going to find that the strength of the attractive force in magnesium oxide is stronger because there's a greater charge difference between a +2 and a -2 than there is between a +1 and a -1. The next strongest is a metallic. Then we get into moleculars. So for the moleculars, part of what I am going to have to look at is what kind of intermolecular forces do I have, right? Do I have LDF? Do I have dipole-dipole? Do I have hydrogen bonds? Generally, we find that the more forces we have, the stronger it's going to be, and the less forces we have, the weaker it's going to be. Is that always true? No, it's definitely not always true, right? If you think about oil, right, we often cook with oil. Oil boils well above 100 degrees, which is where water boils. But water has London dispersion forces, dipole-dipole, and hydrogen bond. Oil only has London dispersion forces. Yet that one London dispersion force is stronger than the 3 in water. Okay, and that's just because it's such a large molecule, it has so many electrons, its London dispersion force is stronger than the other 3 combined in water. However, generally when we ask you to rank, they're usually going to be pretty straightforward. We're not usually going to give you those weird exceptions because there isn't necessarily a way for you to know when it switches over from 3 is stronger than 1, okay? So yeah, we're going to look at those intermolecular forces, and from there we're going to kind of decide where it falls. So once we've decided what kind of molecule it is, and if it's molecular, we've assigned what type of forces it has, we're usually able to rank from there. So when we're ranking, if we're going to go from highest boiling point or melting point, it really doesn't matter, all the way down to the lowest boiling point or melting point. So we're going from highest to lowest. We are going to find that our network solids are always going to be highest. Then it's going to be our ionics, where we're looking at biggest charge to lowest charge, right? If we have multiple that we are ranking. Then it's going to be our metallics. And then it's going to be our moleculars. And when we're ranking our moleculars, we want to look at what are intermolecular forces. So we're generally going to find that if we have a hydrogen bond, that is going to place it higher than something with a dipole-dipole. And that's because to have a hydrogen bond, you also have to have a dipole-dipole. So generally it's going to be higher. Okay, our London dispersion forces, we're just going to throw them off on the side. And that's because, like I talked about, they can vary in strength from strongest to weakest. And if my molecules that I were comparing both only have London dispersion forces, then I want to look at the number of electrons, right? We talked about how the strength of the LDF is dependent upon the number of electrons. And if those are too close to call, then I want to go ahead and look at shape, where that more linear shape is going to be higher. So yeah, you're going to have to rank some things. So we can look at an example of ranking. Okay, so let's rank the following from highest to lowest melting point. So we have water, we have methane, we have sodium chloride, we have calcium oxide. So we want to start by figuring out what kind of molecule is it. So if we have water, water is going to be a molecular compound. Then we have CH4, right? CH4 is also a molecular compound. Then we have sodium chloride. Okay, this is ionic. And then we have calcium oxide, which is also going to be ionic. So if we think about the ranking that we set on the previous slide, we said it goes network solids. We don't have any of those. Then it goes ionics. So we have two ionics. We have sodium chloride, we have calcium oxide. So to be able to rank between the two of them, I want to look at what kind of charges do I have. So NaCl, we have a +1 and a -1. In CaO, we have a +2 and a -2. So because we have larger charges, the calcium oxide is going to be the highest. And then if we go from there to the next one, it's going to be the sodium chloride, right? Because the two ionics are going to be higher than the two moleculars. We know the calcium oxide is going to be above the sodium chloride. So now we get to water and methane. So these are both molecular compounds. So if one was metallic and one was molecular, then I could have said, oh, the metal comes here, the molecular comes here. But in this case, they're both molecular. So I'm going to have to look at what type of intermolecular forces do I have. So if I have water, water is going to have all three, right? It has London dispersion forces because all moleculars do. It has a dipole-dipole because water is polar, right? Water is bent. When we talked about shapes, we said bent was always going to be polar. And it's going to have a hydrogen bond because the H is directly attached to the O. So now if we go over and look at methane, so again, it's molecular, so it automatically has that London dispersion forces. We next need to decide if this is polar. So methane, if I were to draw this out, has a tetrahedral shape, carbon in the middle and 4 hydrogens around it. Because it's tetrahedral and all the non-centrals are the same, this is a non-polar molecule, which means it only has London dispersion forces. So now if I want to rank between water and methane, water has all 3, the methane only has 1. So our water is going to come next in our list, and then it's going to be our methane with the lowest. Okay, so figure out what they are. Once you've decided what they are, you may be able to rank from there. If you have to do further work, like decide what type of intermolecular forces there are, or decide what kind of charge differences you have, then go ahead and do that. Okay, but that is how you are going to go about ranking melting points and boiling points, is look at the different type of forces that are holding your molecule together, and from there you should be able to rank them. So if we look at this chart here, we basically have boiling points for a lot of really common hydrides, okay? And hydrides because they all contain hydrogen in them. So you'll notice we've kind of grouped them together by group 14, group 15, group 16, and group 17. These groupings also correspond to the shapes that we have. But if I look at group 14, which is CH4, SiH4, GH4, and SNH4, these guys here all have a tetrahedral shape. Right? If I look at group 15, which is ammonia, PH3, ASH3, and SBH3, these all have a pyramidal shape. And then if I look at group 16, so water, H2S, H2SE, and H2T, these all have a bent shape. And then finally we have group 17, so HF, HCl, HBr, HI. These all technically, we consider them to be linear, even though they're not really the regular linear that we talk about, because normally we talk about linear with respect to 3 atoms. But these are going to be linear with respect to they're just 2 that are going to be attached in a straight line. So why these shapes matter? Well, those shapes come into play with determining how strong those intramolecular forces are, right? These are all molecular compounds that are on here. So if we want to compare them, if we think about this tetrahedral shape, these are all going to be nonpolar molecules. So they all have only LDF. If we look at the pyramidal, right, because those are kind of the next group, these are going to have LDF, because they always have LDF, but pyramidal has a lone pair on the central atom. So it's going to have LDF and a dipole-dipole. And we're actually going to find that one of them has a hydrogen bond, right? And that one with the hydrogen bond is ammonia, because N is one of our highly electronegative atoms. So we can say H bond in NH3, right? And then if we look at this group, we have the same idea as what we had with pyramidal, right? We're still going to have LDFs because they all do. They're all going to have a dipole-dipole because they're all bent. And then in water, we also have a hydrogen bond. And then we have our last group of HF, HCl, HBr, and HI. So again, these are all going to have LDFs because they're all moleculars. They're also all going to have dipole-dipole because the hydrogen and the chlorine or the fluorine or the bromine, the iodide don't have the same electronegativity. And then we're going to find that we have a hydrogen bond in HF. So all of these intramolecular forces kind of explain why we find things where we find them, right? So our tetrahedrals were the only ones that have LDFs. So that's why they're the lowest, because they only have one intermolecular force. When we look at these other ones, they all have LDF and dipole-dipole, which is why they show up a little bit higher. When we look within the individual groups, we see that the first ones of NH3, HF, and H2O are all higher than the remaining ones in their groups. And that's because these three have hydrogen bonds. So water has an H bond, a dipole-dipole, and an LDF. Whereas when I get to H2S, it only has a dipole-dipole and a London dispersion force. H2SE, again, only a dipole-dipole and an LDF. And H2T, also only a dipole-dipole and an LDF. So you'd almost be tempted to say, well, then why aren't these three kind of in a straight line? And that's because they're London dispersion forces. If you go from a sulfur to selenium to tellurium, these have way more electrons. So what you're finding is that as we go down the group on our periodic table and we add more electrons, the London dispersion force gets significantly stronger, which is why these guys are going to be so much higher and why they all kind of go up. The only ones that are kind of wonky are these three at the beginning, and that's because they had those hydrogen bonds. And then as those hydrogen bonds went away, then it kind of went back to that regular going up. So why is the water higher than the HF and the NH3? Has to do with the shape. Water has the ability to make more hydrogen bonds and more dipole-dipole attractions just because there's more openings around it. Whereas if you think about ammonia, there's definitely more of a specific alignment that we need between our molecules. It gets a little bit more challenging to get to that, okay? So, important to be able to recognize that we can use intermolecular forces to explain why something might have a higher boiling point or melting point than something else. So anytime you're asked to explain why is something higher, we're always looking for you to go to the intermolecular forces. Sometimes you guys are like, well, because the sheet of paper tells me that it's 50 versus 20. Okay, we're not asking for that when we ask you to explain why. We're asking for you to use the theory, which is what this unit is all about, to explain why it's a 50 and that one is a 20. We're not looking for it's just 30 degrees higher. We want to know actually why it is the way it is. And the way we explain that is using intermolecular forces. So really important to make sure that you're able to recognize what type of forces you have to then be able to rank things and explain why something might be higher, right? So we have to be able to recognize if something's a network solid, if it's ionic, if it's a metallic, or if it's a molecular. If we're recognizing it's molecular, we then have to be able to recognize what type of intermolecular force we have so that we can then go about ranking it. Okay, and this is why some of you struggle with bonding, because by the time you get to the end of the unit, everything kind of builds on everything else. And to be able to be good at the stuff that we do at the end, you have to have a really strong grasp on everything that we've done all the way leading up to it. So really important that if you've kind of struggled with something, you go back and you revisit it. And if you find that you're having trouble ranking things, try to see if you can piece together what part is it that you're struggling with. Are you struggling with the intermolecular forces? Are you struggling with recognizing, ionic versus molecular? Where is that challenge happening? And then try to go back and piece it together from there.